Okay, for what we have, the Math 171 Test 4 Review Part 1 handout. Okay, we're looking for the inverse function as well as the domains and ranges of the original function and its inverse. For item number 1, we have a given function f of x is equal to 2x plus 3 over 5. And if we look for the inverse, okay, now f of x is a functional notation for what we otherwise say is going to be y. So we have that y is equal to 2x plus 3 all over 5. And as we cross over to the stage of finding out what the inverse is going to be, okay, now we're going to interchange the x and the y variables. Okay, so we have in the rewrite, okay, we're going to have x is equal to 2y plus 3 all over 5. And we're going to write this statement in terms of y equals. Okay, so we have solving in terms of y equals. If I multiply this equation by 5, okay, so we're going to have 5x is going to be equal to 2y plus 3. And getting the y term, which is 2y by itself, if I take 3 away from both sides, so we have that 5x minus 3 is equal to 2y. And again, to express in terms of y, okay, so taking half of the expression, okay, so I have 5x minus 3 over 2 is equal to y. And we had that y is equal to 5x minus 3 over 2. And we're going to have for the inverse function, again, so we have 5x minus 3 all over 2. And for what we have in terms of taking what we have for the domain and the range. Now, if you notice, we have a fraction for f of x, but we have x in the numerator, and there's no way that we can have the denominator to be 0 since that is locked in at 5. So we can say that for the domain of f of x, okay, that is going to be the same as what we have for the range of the inverse. In other words, what is allowed in x for the function will be allowed in y for the inverse. And so in this case, we're going to have the set of all real numbers. And likewise, okay, for the inverse, we have with the domain of the inverse. And again, we have a non-zero denominator, so we can plug in anything for x, whether it is 0, negative, or positive. And so we can allow anything in the real number system for x in the inverse, and that means we can allow anything in y for the original function. So in this particular case, for what we have throughout, once again, is going to be the set of all real numbers. Okay, for what we have in the case in number 2, we're looking for the inverse function as well as all the domains and ranges of the function and its inverse. And we have for number 2, we have the f of x is equal to the square root of 2x minus 4. And again, for what we have here, f of x, again, is a functional notation for what we're going to say is y. Okay, and now just some things we can mention early on. Okay, now we have a radical function, and since we're working with the real number system, now again, 2x minus 4 cannot be negative. Now it can be 0 and it can be positive. And just taking what we have as an inequality, okay, we have that 2x minus 4 can be greater than or equal to 0. And we have that 2x is greater than or equal to 4. And we have, with division by 2, we have that x is greater than or equal to 2. And also, we have another situation here. Okay, now we have y is equal to the square root of 2x minus 4. And again, okay, by the principal square root rule. Okay, remember, the square root of an expression cannot reduce to a constant that is negative. Okay, so you have by the principal square root rule. Okay, so we have in effect, okay, so you have that y is equal to the square root of 2x minus 4. And again, whatever we have for the square root of 2x minus 4, it cannot reduce to anything that is negative. Okay, so y is the square root of 2x minus 4. And this expression can be equal to 0 or to any value that is positive. So in this case, we have that y is greater than or equal to 0. Okay, and so just to mention, okay, now we can go ahead and take care of all the domains and the ranges. Now we have, in the case of the domain of f of x, for the domain of f of x, okay, now we have for the domain of f of x, okay, you have the set of all values of x greater than or equal to 2. Okay, and so we have, in this case, we have symbolically, okay, we have going from 2 on out to infinity, and what we can have in x for f of x, we can have in y for the inverse function. And so for what we have in this case, okay, so you have for the range of the inverse function, okay, you're going to have, again, you have the set of all values of y such that y is greater than or equal to 2. And we have going past 2 on out to infinity. All right, now, and just sort of tying in, okay, going ahead and taking care of the other domain and range portions. Okay, now we have, you know, for the range of what we have in the function. Okay, so again, we have symbolically, we have the set of all values of y, such that y is greater than or equal to 0. And in interval notation, in case you have, again, values of y going from and including 0 on out to infinity. And guess what? What we have in y for the function, we will have in x for the inverse. So we want to have here, have the set of all values of x such that x is greater than or equal to 0. And again, so we have values greater than or equal to 0. And again, going continuously on out to infinity. All right. Now, in looking for what we have in the inverse of this particular given function, okay, for the inverse, again, we're going to interchange x and y. Okay, so we have the x is equal to the square root of 2y minus 4. And if I square both sides, again, we have the x squared is equal to 2y minus 4. And if I isolate the y term, so we're going to have adding 4 to both sides. Okay, so have x squared plus 4 is equal to 2y. And taking half, we have x squared plus 4 divided by 2 is equal to y. And this y is going to make reference to what we have in the inverse. So the inverse of f of x is going to be equal to x squared plus 4 all over 2. And in looking at what we have from a graphing perspective, and I'll show you both functions and their inverses. Okay, for what we have for y is equal to 2x plus 3 and y is equal to 5x minus 3 all over 2. Let's say that if I just insert some values, okay, now a function and its inverse will have interchanging x and y values. Okay, so we have like among our points for y is equal to 2x plus 3 over 5. Okay, we have among the order pairs, you have 0, 0.6, 1, 1, 2, 1.4, 3, 1.8, and 4, 2.2. Now, our function and its inverse, again, will have interchanging x and y values. Okay, so we have, we have 0, 0.6 for the first function. The inverse will have the reverse. Again, we have 1, 1. And if I put in 1.4, okay, so I have 1.42. We have 1.83 and 2.24. And a function and its inverse will have symmetry with respect to the line y is equal to x. So I'm just going ahead and kind of put these down. Notice you have the interchanging of the coordinates. Okay, again, so a function and its inverse will have symmetry with respect to the line y is equal to x. And once again, the x and the y values will be interchanged. Okay, for y is equal to the square root of 2x minus 4, and y is equal to 1/2 of x squared plus 4. Okay, now I have the added condition that x is greater than or equal to 0. And I wanted to show that we do have symmetry with respect to the line y is equal to x. And the reason I'm adding in this condition for the inverse is that if I went by just the function alone and said that the domain of the inverse would be the set of all real numbers, notice I would have this left half of the entire parabola that represents 1/2 of x squared plus 4. And strictly speaking, that's not going to be the inverse. In fact, this is going to be too much to be unequivocally the inverse of the square root of 2x minus 4. So to represent this portion, I have to, again, just trim off the excess here. And so for what we have throughout, again, you have the x and y values interchanged throughout, and symmetry with respect to the line y is equal to x.